determining normal probabilities. So here we're going to have a look at using the curves to find probabilities from a normal distribution and how to use the symmetry properties of the normal distribution. Now, before we get going on the theory, when you're thinking about probabilities with a normal distribution, it's really important to draw a sketch every single time of what we're actually looking at. So I'm going to do a quick quiz with you. Each time I'm going to give you a probability. So this is probability that Z is less than negative 1.2. You've got to decide which diagram best represents that. Don't worry about the little notches at the bottom. The scale will change each time, but this is the standard normal distribution, so the mean is always 0. So which one of these diagrams represents the probability that Z is less than negative 1.2? Hopefully, you think it's this one. That's correct. So I'm going to just go through a bunch of these. Each time, decide which one is the best representation. So here, this question and the next ones are slightly different. So which of these represents a probability that x is less than a equals 0.34? Now remember that the area under the curve represents the probability, and that the sum of all of the area under the curve, I didn't need to say the word sum there, the area under the curve is 1 because all probabilities have to add up to 1. So if that's 1 and we know that it's symmetric about 0 here, then we know that this is a half. So the probability that x is less than a equals 0.34, B represents that. Okay, so let's have a look at how we can use our CAS to find the area under a normal curve. So we're using Z being our standard normal random variable here. That means that our mean is 0 and our standard deviation is 1. We're going to first have a look at finding what's the probability that Z lies between negative 1 and 2.5. So I go to Menu, Probability, Distributions, Normal CDF. My lower bound is negative 1, that's here. My upper bound is 2.5. Then my mean is 0. My standard deviation is 1. It gives me my answer. Let's think about what that means with my curve. So I've got my axes here. I draw a curve trying to make it as symmetric as possible. I know that this is 0 because it's the standard normal random variable. So I'm looking from negative 1 to 2.5. And then I'm just going to shade in that region to show this is the bit that I'm interested in. And that's it. Looking at part B, the probability that z is greater than 1. So 1 is my lower bound, and then I need to go up to infinity. You can find the lemniscate, the infinity symbol, in the pi menu. That's the button with the pi on it. So this is what I get for my probability. Remember, when we're giving probabilities, we tend to do it 4 decimal places. Let's draw a sketch. Here's my curve. Probability that z is greater than 1, so this is 0. Here's 1, and it's everything above 1 that I found there. Pause the video now while you have a go at these questions. Okay, we can also use the CAS to determine percentiles of a normal distribution. So here, x is normally distributed, my mean is 100, my standard deviation is 6. I need to find a value k such that the probability that x is less than or equal to k, remember this is the same as this because it's a continuous distribution. The probability that x is less than k is 0.95. Let's think about what we're going to be expecting. Here's my normal curve. I want the probability to be 0.95, so my k is going to be somewhere up here. The area under the curve is 1. 0.95 is not far off 1, so this is my k here that I'm trying to find. So I go to menu probabilities distributions again, and this time I'm going to use inverse normal. I say the area I want and my mean and my standard deviation, and it tells me what value gives me those properties. And so remember, if this is my mean at 100 there, then I'm expecting k to be bigger than 100, which I've got. Now have a go at questions 5 to 6 and 9 to 11. Make sure you mark your work. I can also find 2 values, so in certain cases. So I've got the same normal distribution as I had before. Now I've got 2 values, C1 and C2, such that x is in between them, such that the probability that x lies between C1 and C2 is 0.95. Now, there are an infinite number of regions that have an area of 0.95 under the normal curve. But what we do is we find the one that's symmetric about the mean. So here's my mean. That's a rubbish straight line. There's my mean, 100. And because this whole area is 0.95, this bit plus this bit must equal 0.05. Because I'm symmetric about the mean, I can just divide 0.05 by 2 to get that the area of this part is 0.025 and this part here is 0.025. Then I do menu probability distributions inverse normal for 0.025 for the area for this part. When you're doing inverse normal, it only does probabilities less than a certain amount. So it can do this to find C1, but then to find this C2 value here, I need the area of all of this part. So that's 0.95 plus 0.025. That's where 0.975 comes from to get C2. So, symmetry properties that we can use with our normal distributions. The probability that z is greater than a is 1 minus the probability that z is less than a. Remember, less than or equal to, same thing for normal distribution, not always. Not for discrete random variables, but for normal distributions, they're interchangeable. Probability that z is less than negative a is equal to the probability that z is greater than a. So in this diagram here, my negative a, which is going to be positive in this case because we've got a mean of 100, but actually maybe it'd be easier to do this. When I have my standard normal variable with this at 0, negative A and positive A is the same area above the positive A as there is below the negative A. The probability that Z lies between negative A and positive A is equal to 1 minus 2 times the probability that Z is greater than A, or 1 minus 2 times the probability that Z is less than negative A, because these areas are equal. Now you can do questions 13, 15 and 17. Remember to mark your work.